Hey, good morning or good afternoon, depending on where you are in the world. And welcome to our webinar, Fuel AI Success with the Right Data and the Right People. I'm Abby Lundberg, Editor-in-Chief at MIT Sloan Management Review, and I'll be moderating the event. Today's program is sponsored by SAS. It takes a lot to build and deploy AI models that work well. But when organizations put too much focus on the technology and the algorithms, they often overlook other key needs, and this puts their programs at risk. Part of this is a leadership issue. Business leaders who take more ownership of their AI programs increase their likelihood of success. This starts with identifying the right data to train and operate their models. This isn't something to delegate to the data team. They ask the right questions and know what answers to look for. And they include the right people, not just technologists and data scientists, but a diverse set of professionals with a range of perspectives. Our speakers today have written about these topics for MIT Sloan Management Review. We'll post those articles in the handout section for download, and we'll also post the links in the chat. Roger Hurl is the Brate Peschel Professor of Statistics at Union College in Schenectady, New York, and co-author of Leading Holistic Improvement with Lean Six Sigma 2.0. Tom Redman, also known as the Data Doc, is president of Data Quality Solutions and author of People and Data, Uniting to Transform Your Organization. Welcome, Roger and Tom.
I'm delighted to be here. And thank you for everyone for taking time out of what, if you're in the Northeast, is the last week of your summer. And if you're other parts of the country, well, just out of the work week, but really to join this webinar. Roger and I have been working for a long time together, and we started really trying to dive into a topic that sort of bothered us. It's why is progress in data science so slow? It seemed to us that the conditions for things going much faster have been in place. Certainly the computing capability, better computer programs, more and more trained data scientists, business needs, and so forth. But why does progress seem so slow? And we've worked together to try to understand, revisit our experiences and see, well, what worked and why, what didn't work and why, and spin our experiences in different ways. And every now and then what's happened is a real point of light has emerged, a real light bulb has gone off. And usually when that happens, we kind of look at each other and go, gee, why didn't we think of that before? And as Abby mentioned, there's some paper and some details that you can read. We're going to try to expose the light bulb going off on two interrelated problems here today. The first problem is quite generally, data quality does not get the attention it deserves in AI. I'm going to kind of explain a little bit more about that. Quality consists of two components: the right data and is the data right? And frankly, neither gets the attention it deserves, but the right data stands out as getting far less. And we really want those who are serious about AI to extend far, far more effort into attacking these problems and into attacking the right data criteria. And the second problem is if you think about AI, so what are we doing? Well, we're kind of turning over trust in a model that was developed using a black box that no one understands, trained on data that no one trusts. And, is that really the kind of thing that we want to do? And so we're going to try to emphasize three important points here. The first is this notion that high quality data, there's two components to it. Is the data right? Most people are familiar with that, and the right data. And I'll explore this in a little greater detail. The second point is both these problems we've laid out are hard, but statisticians bring a tool set to bear that can really help with both problems. And we want to explore that a little bit. And the third thing that we want to talk about is there's sort of a management 101. Who's in charge? What are the management responsibilities? And there's a temptation to think, oh, okay, well, that's a modeler's responsibility to get the right data. But we want to be insistent that no, this is the managers, not the modelers responsible for the right data. Now, of course, I mean, if you're listening to this, you probably know that all is not well in the world of AI. You can sort of, pick your favorites. I just want to make a point about the last one. We appear to be getting past the peak on the hype cycle. And last night I was reading some interesting work actually done by The Economist on, does the Gartner hype cycle actually hold? And they could, found some examples where it did, and then far more where it didn't, where the hype concludes in no progress whatsoever. And it bears mention that we've had previous AI winners, depending on how you count, between 2 and 5 maybe, and we certainly don't want data quality to be a big contributor to an AI winner, and this basis of inference, we don't want that to be a big contributor as well. So part of our motivation here really is that. All right, let's dig into data quality, and I want to do this via vignette. If I may pick on Abby for just a minute, and this vignette unfolds when you're on your way home, driving home from a particularly stressful day, and you get a call. You look at your mobile phone and you see, oh, that's my kid's school. You pick up the phone and the person says, Ms. Lumberg, my name is Ms. Jones. I'm the principal at your kid's school, and they were in a fight today. And so we have a no tolerance policy. So, by the way, they may have even been trying to break up the fight, right? But we have a no tolerance policy. You're involved in a fight, it's a week suspension. So your kid's suspension starting tomorrow. They're welcome back a week from tomorrow. And what became a bad day, what was a bad day, become way worse, and your mind's racing. What went on? What am I going to say when I get home? And so forth. But when you do get home, you call the kid down from their room and you innocently ask, well, how was school today? And the kid responds, Mom, it was great. I got an A- on my Spanish test. Right now, what are you thinking? Right. So what's going on in your mind? Right. You don't actually doubt that they got the A-, but that's not what you were really asking about. And you're pretty darn sure that they know that's not what you were asking about as well. So maybe you remarked, the principal called, said you were suspended. Let's dissect this a little bit. And the dissection looks like this. First of all, I mean, quality is always in the eye of the beholder, right? Quality, Abby is judging the quality of the kid's response. I mean, this is quite generally true. The person, the application, the team, whatever it is that is using the data, judges whether the data is of high quality or not. And all real problems have two components to them: the right data, the data that's actually needed. In this particular case with the kid, it says, well, what went on in school around suspension? That's the data that was actually needed. And then again, is the data right? And in every real problem, these two basic series of dimensions, these two kind of features are always important. There may be other features that are necessary. So sometimes, is the data formatted in the right way? Everybody's familiar with barcodes, which provide some basic data about the product that's being built. That's not formatted so that an individual can read it, but so that a scanner can read it. And an AI, and so we come across times when things need to be formatted as vector databases, right? So now I don't want to, right? We're going to concentrate here on the right data, and I'm not saying that it is more important than the data being right, and that both are important, but some dominate in different situations. And the reason we're bringing up the right data is it has gotten short shrift in discussions about quality with respect to AI. So with this background, Roger and I put together this little thing we call the right data framework, and it works this way. All good work in AI and quite generally in data science starts with a good definition of the problem. What is it that we're trying to solve, including what's the population that we're interested in? It's something that people may not think about that, too much, but we're trying to build a model. Is this model supposed to work in the Northeast? Is it supposed to work in all of the United States? Is it supposed to work in America and South America, right? Is it supposed to work for both men and women, and so on? And so this question of what are we trying to solve for and who is always very important. And you really have to do, it is essential that good work be done there, and that all agree on the problem of interest. It's easy for modelers to have one view of the problem and business people to have another. And then the second step is hard work to work through the right data criteria. And from that, design the data that we need, the right data to address that problem for that population. I'm going to go through some right data criteria in just a minute, right? So then, with those criteria in mind, you judge the training data, and it is very easy for modelers to fall in the trap of getting the data that's easily available. And so when you smack the data that you have that you're proposing to use for training data against the right data training criteria, then a lot of times you find big gaps and you find out, no, this is not the data that we need at all. And of course, when that happens, managers should send modelers back to find better data in the sense that it better meets the criteria. Step 4, the work that everybody loves, developing the model, developing the algorithm, and then the model gets turned loose. The future data is so once you have a model, you actually apply it, and it's applied to future data, and maybe the model gets retrained, and it's easy to apply the model in situations beyond that in which it was contemplated for use. And then the model may no longer apply. This famous example of this involved the Tay chatbot, right? So these 5 components go together in this framework, and I want to dive down a little bit into items 1 or 2, and so let's just take a look at some sort of typical example. We need to improve our process for evaluating loan applications, and it's kind of a good high level statement, but dig down and what does it really mean? And of course, getting this right is intimately tied to the right data. And so if improved just means, well, we want to do what we did before, but we want to do it cheaper, then the data you have, the previous data on loan applications, that data will probably be fine. If instead you're concerned about bias throughout the process, then you're going to need data that's less biased. That may be hard to come by. If you need, if improve means we need to be able to explain the answers a little bit better. So AI is famous for not being too explainable. It may not be the right solution for you for that particular problem. Another definition of improve could be, well, we want more performing loans. A performing loan is one that people pay back and on time, and fewer non-performing loans, which is, it's pretty obvious those are loans that people don't pay back or don't pay back on time. Well, remember, the data you have is the data for the loans that you granted. You don't have data on the loans you didn't grant. And so, if you want more performing loans, that means you're going to have to have data on those loans that you didn't grant. So you're going to have to figure out a way to get that kind of data, or you're going to have to figure out something entirely new. So that's what the intimate tie between the business problem and the right data criteria are so important. I'm going to follow up a little bit on this performing loans on on the next slide. So we've identified 6 of what we call these foundational right data requirements, and if you're serious about AI, I really urge you to dig into our article on this and understand them in some detail. I mean, at a high level, it's obviously the training data needs to be relevant to the problem that you're trying to solve. Ideally, you have a complete set of all the data that is relevant to the problem you're trying to solve, and even ideally beyond that, you don't have anything that's irrelevant. But the criteria there is really you have as much as you possibly can of data that is relevant to the problem at hand. And comprehensiveness and adequate representation really is about, do you have data for training purposes that covers the whole population of interest? And I brought up the problem earlier that if you're trying to get more performing loans, you don't have data on the loans that were denied. So those people who didn't get loans that you're thinking about, may get in and improve your performing loan statistics. You do not have that data. That's what this requirement is all about. Freedom from bias, I think most people are pretty familiar with it. Biased algorithms make the news all the time. In some cases, timeliness is important. In some cases, really clear definition of what the data is all about is really important. And then appropriate exclusions is a catch-all bucket for so people may have opted out in their personal information being used in any sort of modeling going forward. And so exclusions aims to make sure that those who have opted out, or some, maybe things that are illegal to use or whatever, are not included in the analyses going forward. And I really want to make clear, I mean, we view each of these requirements as tough. So for most people, they will be unfamiliar, right? And now in any problem, you may not be worried about bias, or you may not be worried about time and so forth. But it is a smart move to work one at a time through each of these requirements, specify exactly what you need to address the problem at hand, and then compare the data that you're proposing to use against these requirements. Now, let's do a poll. Which profession would you think is best suited to helping clarify and address these right data criterions? Maybe you've heard some hints throughout the presentation, but is it computer science? Is it applied math, statistics, data science, or engineering? And as you complete this poll, I'm going to turn over responsibility for this webinar to Roger.
Great. Thanks very much, Tom. I appreciate it. And we'll give you a little more time to vote in the poll. You should be able to see on your screen how the votes are building. And we'll give it a few more seconds, see where people come out. Okay, let's go back to the slides. In our poll, we saw that data science won. Tom and I are going to actually make a counter argument. We're going to argue that the correct answer is statistics. Now, Tom and I are both statisticians, so we will confess there's a little bias on our part, but we think we can make a solid case that the true answer really is statistics. The reason is there's some unique technologies that statistics brings to bear around understanding the right data. These are just a few of them. This is not everything. But design of experiments is actually a subdiscipline of statistics that's totally focused on figuring out how can we get the best possible data to answer a specific question. So design of experiments, the thought processes that go into saying, here's our problem. Now, what data could we use? What's the best possible data we could get to answer that question is extremely helpful. Now, you might be surprised to see statistical process control, but this is a methodology to look at the stability of processes over time. As Tom mentioned, timeliness is a big issue, especially in financial applications. 3-year-old data may be totally irrelevant. So statistical process control helps us understand stability of processes and when the right time frames might be to collect the data of interest. Now, we said Bayes' theorem. Bayes' theorem, many of you know, is really about conditional probability, the probability of A occurring given that B has already occurred. We can extend that a little bit to talk about Bayesian methods in general. Bayesian methods allow us to integrate domain knowledge or subject knowledge directly into the estimation process. So in addition to getting the data of interest, I'm sorry, the slide moved forward. I'm going to put it back there. In addition to getting the data of interest, it also tells us how to incorporate the domain knowledge or subject matter knowledge that we already know, which is a huge advantage if we have significant subject matter knowledge. Now, along the same lines, Tom and I also feel that relative to domain knowledge and subject matter knowledge, we have to be very careful that we don't walk away from the scientific method. The scientific method, of course, is one of the greatest intellectual achievements in the human history. It replaced things like gods and goddesses, astrologers, oracles of Delphi, and things like that. The reason we bring it up is it's well known that AI lacks common sense, if I can use that term, in domain knowledge. Now, one example you can Google, there was a humorous case several years ago of where Amazon's automated pricing algorithm priced an introductory biology book at $4 million. Now, it was not a rare edition. It was just a regular biology book. Now, any 10-year-old could tell you a biology textbook will not sell for $4 million. That's common sense. But AI knows what's in the data. Whatever's not in the data, it's not going to know. Now, this quote, we talk a little more about Ali Rahimi in the article, but he's basically saying there's a distinction between a machine learning algorithm that's a black box and a whole discipline that started to become a black box. Tom and I, and he alluded to this at the beginning, we don't want to replace the scientific method with a black box that nobody really understands and can see inside, that's trained on data that either maybe we don't trust or perhaps we shouldn't trust it. Maybe we do, but we shouldn't. This leads to what we call a basis for inference gap. What that means is if we fit a machine learning model or an AI system on a given set of data and it works really well, that's great. How can we be confident that it will work next week on a different set of data that was collected at a different time frame under a different set of circumstances? On what basis can we make that inference? That's the point that we're actually talking about, and that's a big issue with AI. And we don't have time to get into it today, but we point out in the article that doing out-of-sample testing on one data set is not sufficient because the test data and the training data are really both part of the same data set collected at the same time frame under the same circumstances. So we really need additional data. We think statistics can add to what we already have, can basically balance out the team, balance out the technology, because statistical models by definition are simpler and they have real world interpretations. So I assume everybody on the call has fit a linear regression. If the slope is 5, it says when X1 increases by 1, we expect Y to increase by 5. Now that's simplistic. We can do better than that, but at least it's interpretable and I can use my domain knowledge to say, does this really make sense or not? Or is this basically inconsistent with subject matter knowledge? It gives us a way of testing subject matter knowledge. Another thing that statistics can do by integrating probability in a very formal way is we quantify uncertainty. Another issue with AI, as we know, is that it can be very confident even when it's wrong. I used Chat GPT just to test it out, and I asked it, who is Roger Hurl? And it said some things that were correct, but then it said I was senior vice president for Baxter International, which I've never worked for. I have no idea where Chat GPT got that from, but it didn't quantify the uncertainty and say there's a small chance this could be true. It just stated it as a fact. So we always want to quantify our uncertainty. Randomization is perhaps the biggest contribution of statistics in history, in its history. And this basically means we randomly allocate some kind of treatment to objects of interest. For example, clinical trials are done in a randomized way. If you participate in a clinical trial, they'll randomly pick who will get the treatment, who will get a placebo or other treatment. That provides a great basis for inference because it prevents the possibility that there's some other variable, a lurking variable that's actually biasing our results because we did everything randomly. A/B tests, which I think we're all familiar with, are one example of applying randomization to AI, and that's why A/B tests tend to work. Tom and I actually recommend that people consider developing a statistical twin to go along with the AI system or the machine learning model. Now, you're rarely going to beat an AI system or machine learning model for accuracy of prediction or classification. They're just way too good. However, if you also have a statistical model that's tailored, calibrated to the AI model, then we have the best of both worlds. We get the best possible prediction, but we also get some degree of interpretability. Why is it predicting a particularly good or bad result there? And we can test that relative to domain knowledge. Now, most of you are no doubt familiar with the concept of digital twins in Industry 4.0, where we have a physical system that may be very complex and hard to understand, but we try to mimic it in a model, in a digital twin, so that we can play what-if games and try to understand cause and effect relationships, even when it's a very complex system. Now, back to the Management 101 point. Tom and I are repeating something you know already. So we don't claim to have figured this out. This has been known for a long time. Managers are ultimately responsible. We know that we can delegate authority, but we can never delegate responsibility. So if the model blows up, the people that are going to be called on the carpet and have to give an explanation are those in charge, the managers. So in our experience, we've seen a little too much delegation from managers to technical people. This could be because the manager doesn't have as deep a technical background. But in any case, we think it's very dangerous. And here's why. And by the way, Tom and I are both technical people, so we're not against technical people. There's an old saying, I think it goes back to George Box, that modelers, like artists, have a bad habit of falling in love with their models. Now, in AI, that means if people spend months, maybe a year, developing a machine learning model or an AI system, naturally, they're going to feel very good about this system. And telling them their model isn't that good is kind of like telling new parents that their baby is ugly. It's not going to go over very well. So to get around that problem, we can't just ask the developers, hey, how good's your model? They're always going to say, oh, it's great. It's going to work. So what we're saying is that managers need to step up and assume the responsibility, not delegate it. Obviously, work with the technical people, but don't delegate the responsibility to figure out what's the right data for this problem. And as Tom made clear, the right data is not the same thing as big data. If you have the wrong data, if you have biased data and you get a lot more of it, that's not going to give you good solutions. You're just going to be that much more biased because you have a lot more biased data. So really the managers have to ask the objective questions. Well, how do we know that this is the right data to solve this particular problem? So we recommend that you ask penetrating questions throughout the process, not just at the very end, but from the very beginning when we're defining the problem, we start asking questions. And we recommend people with statistical skills, whatever their terminal degree, people with statistical skills, not to replace computer scientists and data scientists and others, but really to augment them on the team. In our articles that you'll have access to, we wanted to highlight some of the questions. What you're seeing here is just a sampling of the questions that we have. During problem definition, we want to start asking tough questions because if there's an issue, we want to find out early, not late. So a great question to ask is, how are you going to acquire training data that meets the right data criteria? Now, this assumes we've agreed on what the right data criteria are, which assumes we've carefully defined the problem. Notice what we're doing here is we're trying to start with the problem, base everything on the problem, and then talk about data. In Tom's and my experience, too often we start with the data. Hey, I have this great data set. What can I do with it? That's putting the cart before the horse in the sense of we always want to start with the problem and then figure out the data to match that problem. And then when we start developing models, we want to make sure that people fully understand the data they have, where it came from, when it was obtained, who obtained it, from where, under what circumstances, has anything been deleted, has anything been modified. In our experience, and I teach a big data course at Union College, students come in with these massive data sets and they start fitting models and they say, wait a minute, time out. Tell me about this data. Where did it come from? Oh, I got it from Kaggle. I got it from the UCI machine learning repository. Okay, that's where you downloaded it, but who acquired this data in the first place? How was it obtained? Under what circumstances? And I tend to get a deer in the headlights look. Well, I don't know, but it must be good if it's on Kaggle. Well, it may be good, but you don't actually know anything about this data, how it was collected. How can you model data if you don't know anything about it? And then before and during deployment, we recommend you force a discussion of failure. Now, nobody wants to talk about failure. However, there's no guarantees in AI. I think Tom made that point pretty clearly. Some very smart companies like Google, Amazon, et cetera, have made some very big mistakes. So we want to force a discussion of failure. It's always a possibility, but let's talk about it up front. Let's get the cards on the table instead of hoping for the best. Let's consciously think about how the model, how the system could fail, so that then we can have a discussion of how to potentially mitigate that. We've had a number of conversations with people when we said, okay, how might this fail? Oh, it won't fail. Trust me, I guarantee you, I stake my reputation. This will not fail. Well, as we know, a lot of times it does. So we just want to have a conversation about it, identify potential failure modes, and put some kind of methods into effect to mitigate those or prevent them. So just to wrap up, I want to go back to the slide that Tom started with a couple of slight modifications. The two things we're really trying to focus on today, there's a lot more we could talk about, of course, but for this seminar, we want to focus on two main things. One is the right data, the fact that it doesn't get enough attention. And as Tom said, the right data is not the same as asking, is the data right? The numbers may be correct, but it's not actually the data that you need. You need very different data collected in a different way. And then secondly, there's an unsolved problem, and we don't have a solution for it, but we have some ideas that AI lacks sound bases for future prediction and inference. Working well on our training data is great. Working well on test sets. That's great, but that's not the same thing as working well with new data collected under different circumstances in a different environment. So the specific suggestions we have for people today is keep in mind the manager's ultimately responsible for. The manager is going to be the one called in on the carpet if things don't work out. So don't delegate your responsibility. Obviously, you want to get advice and input from your most seasoned technical people, of course, but don't forget you're ultimately responsible. So you have to be asking these questions to verify you really do have the right data. And you can be more objective about both the data and the model because you didn't develop it. It's not your baby that you're evaluating. And so you can be more objective. When you evaluate AI systems, we often focus on the back end, on the models, but really we have to look at the front end, the original data that was used to train the system, and evaluate the degree to which it really is the right data for this particular problem. It could be great for another problem, but it's not great for our problem. And then when you put together your AI teams, what we're arguing for is technical diversity. That's an aspect of diversity we don't talk about enough. Technical diversity. We don't want a team that's an inch wide and a mile deep. We want breadth. So of course you need excellent coders, AI developers, data scientists. Of course you need those. In addition, it's great to have some people on the team that understand some of these statistical concepts like design of experiments. With that, we are now going to turn it over for questions, and Abby will be jumping on now to moderate the discussion. Thanks for your patience.
Hey, thank you so much, Roger and Tom. A lot of food for thought, and a lot of the questions coming in are around this issue of roles and who's responsible for these different aspects. So let's start with. And it was interesting. There was sort of a conversation back and forth going on in the chat around this topic. So, for example, Cameron asked a question. He said, unless the statisticians have in-depth knowledge of business and operations, they will miss significant aspects of selecting the right data for the business. And then on the other hand, Daniel says, domain knowledge is critical to building the correct model. However, even if the business is engaged, it's important to make sure the right questions are asked. And then again, Daniel said people tend to favor their area of discipline. Actually, that's a separate issue. So, it was Jenny who said, I'm not arguing with the importance of statistics, but I come from a discipline, ocean and climate, where statistical competence is tightly integrated with the domain expertise. So can you talk a little bit about sort of how those roles break out? And in particular, you talk about team. How does the team work to bring those capabilities to bear if the business owners with the domain expertise don't know how to ask those right questions, or vice versa, if the statisticians don't know as much about the domain?
Sure, I'll comment and then we'll see if Tom wants to add anything as well. As Tom said, it all goes back to the very beginning in defining the problem. And this is an obvious thing that is often overlooked, and different people have different understanding of what the actual problem is specifically that we're trying to solve. Once we've adequately defined the problem clearly, concisely, so that everyone is in agreement, it then becomes a little clearer what kind of skills will be needed to address this problem. So we're not just saying put a statistician on every team. We're not trying to get all statisticians fully employed. That's not the point. The point is, when there's a lack of clarity on the right data, and we need to start thinking about how can we collect data to answer a specific question, statisticians have a lot to bring. Now, the point's correct that several people said, a lot of statisticians don't have any domain knowledge. That's absolutely true. We wouldn't deny that. You absolutely need the domain knowledge. Now, if you have computer scientists, data scientists, statisticians that all have that domain knowledge, great. But in many cases, you'll actually have to bring in a business person who maybe isn't so good in statistics or data science or coding, but has that unique subject matter knowledge. So the point is not counting heads and what people's titles are, but do you have the right skill set collectively on the team to solve this particular problem? Tom, do you want to add anything to that?
Yeah, I would like to add something to it. I think there's a famous quote from Einstein that I'll get, approximately correct, but I think he said that, if he had an hour to solve some problem that would save the world, he'd spend 59 minutes making sure that he understood the problem, right? And part of the reason we're beating on this is there is no easy road to doing this, right? I've spent a lot of time as a statistician wandering into an area I didn't understand at all. And people will tell me what their problem is, and then I kind of go, "Really, is that the problem?" And asking a lot of apparently dumb questions, and then 2 or 3 days later, a new problem emerges, and 2 or 3 days later, after that, another problem emerges, and then maybe we say, "Well, we ought to ask the boss on this, and we ought to get somebody else's opinion on that." And I don't really know of a simple series of steps to nail the problem, right? I to people in the business, they have the problem, right? But a lot of times their statement is, "I need relief from immediate pain," and that is not the longer term problem. And so part of the point of diversity is bringing people who look at it from a bunch of different perspectives. A real great diversity, again, I want to bring it up, is the ability just to ask dumb questions, right? And let things percolate, and take your time on doing this. There is a temptation to want to get into let's start coding, let's start solving the problem, and it is great temptation, and it's not just in technical fields, in all fields. It's this way. So the question about, well, how do we know when we have the right team is you sort of know you have the right team when you've looked at it from a lot of various perspectives, and everybody's going, yeah, this is what we want to solve.
So AJ, just to keep on the role topic for a few minutes, AJ asked, going back to the poll, said, because so many voted data science, can you compare and contrast to the pros and cons of favoring that answer? What is the correct answer to the poll?
Sure. Well, of course, this is an opinion, so it's not a mathematical proof. I can't prove that it's statistics. Data science is a somewhat vague term. Everybody uses it, but everybody usually means something a little different. And typically, this is typical, there could be different opinions in the audience, but we're talking about people who have a strong background in computer science, coding, cloud computing, et cetera, and they also have a strong background in modeling. So depending on the specific data scientist, what their particular background is, it could be a data scientist, but I'd want to make sure they know something about experimental design, that they're used to and have experience in asking the question, what data do I really need to solve this problem? Now, if you look at people that go on I belong to Kaggle, I go to the Kaggle competitions, but one thing that bothers me about them is they start with, here's a data set, see what you can do with this data set. They don't actually say, here's a problem. What data would we need to solve this problem? So it could be data scientists if they had the right background. That's my opinion.
Yeah, let me just build on that a little bit. I mean, so one of the things that I learned as a statistician very early in my career is what's causing the variation, right? I mean, the real world, like the population of interest, it is a highly dynamic, highly variable place, right? And statisticians, not all statisticians, but sort of probabilistically, statisticians are trained to think about variation in the real world. And how are we going to understand that? And how are we going to capture that kind of thing? As opposed to people who are trying to model data, right? Statisticians start with, their playground is the real world. And And often data scientists, their playground is the data. And to the degree it's reflective of the real world, great. But it's just a slightly different perspective.
So Radha, just to follow up on that, Radha is asking, statistics is about probability, then how will it align with AI-based models? You could explain that.
Well, a lot of AI models are probabilistically based. For example, naive Bayes, if you're familiar with that methodology, that's totally based on probability. It's based on Bayes' theorem, conditional probability. Now, that may be a counterexample in the sense that many AI systems do not incorporate probability. So probability is very useful when it comes to quantifying uncertainty. Like, we think this is the right answer, but here's the probability we're wrong. Or we think this is how much return we'll get on this investment, but we could be off by this much. To make wise business decisions, we not only need a suggested answer, but we also need to know how confident are we in that answer and how far could we be off. That's where probability can come to the rescue.
I think that's a really good answer. It's, like even the simplest model comes equipped with measures of uncertainty like percent variation explained or something like that, or confidence intervals or whatever it may be. And I don't know, personally, I find a little bit of humility in that, right? Here's what I think I know, but I know it within a range. And by the way, there's always this possibility that I could be wrong. I think it's part of what makes you able to say this is a basis for of making an inference, because here's our error bounds around that, right? We say the answer is 3, but it's rarely that. It's 3 plus or minus, and it's an enormous contribution of statistics.
So let's talk a little bit about the data itself, getting the right data. And I can imagine that it can be hard to get all of the right data that you need to solve a particular problem. So what suggestions do you have for folks to go about getting as much of the right data as possible, but also mitigating when they can't?
Yeah. So look, can I jump in on this one first?
Yep.
I mean, look, my experience is if you sit down and you think through what you really want, right, then you're able to go after that, right? If you don't think through what you really want and you start with, well, I'm just going to take what's easily available, the question doesn't come up. Now, I've not worked in a real world problem where I got all the right data that I wanted, and I see Roger is laughing there, right? And so with, okay, this is the best that I can practically get, right? And so maybe there's a data set out there that you could get and you think it's going to be right, but it's going to cost $2 million and you can't get budget for it, right? It allows you to really, really think through the trade-offs. And most importantly, to understand the strengths and weaknesses in the data that you're actually going to use. So, look, I mean, AI is so powerful and it's still a computer program, right? And its strengths and weaknesses are going to reflect the strengths and weaknesses in your data. And you must have that conversation, with yourself and among your team if you're going to do good work.
So I just want to piggyback on what Tom said, because I agree 100%. I teach statistics and machine learning at Union College, but before I came to Union College, I worked in the private sector for almost 30 years. I know I couldn't possibly have that long experience. I'm so young, but I did. And one of the things I tell my students is there's no such thing as a perfect data set out there. People often think of data as either right or it's wrong. It's correct or it's incorrect. Well, that's a gross simplification. There's no perfect data out there. And in most cases, as Tom said, we're not going to be able to get exactly what we want. I mean, we'd like to do a clinical trial on every human being on Earth. Well, guess what? We can't do that. So we get as close as possible to the right data, and then we're cognizant of the limitations of this data. We'd have liked to have gotten this. We could only get this. It's not exactly what we need. So when we develop the system, we're aware of its limitations and we're not overconfident. We say this is not likely to work on small loans as well as it works on big loans, or it's not likely to work in Mexico as well as it works in Canada based on the data we have. So part of it is getting as close as possible to the right data. And the other part is being aware of the fact of the limitations in your data.
Right.
So let's, generative AI and LLMs is a hot topic. Can't turn around without reading something about that right now. And so Furman is asking, I feel that this discussion has two levels. One, traditional machine learning, where some of the recommendations are helpful. And two, the elephant in the room, LLMs, models that contain billions of parameters and based on different modalities of, I'm assuming, neural networks and ends. The latter are truly difficult to disentangle, truly black boxes. We're actually using them with little knowledge on how those models are built. So I don't know if there's a question in there, but there's a comment, and would you comment on that?
Well, so look, one of the things that a lot of companies are trying to do is they're trying to augment those LLMs with their domain knowledge, right? Some particular examples is that we have a lot of contracts with suppliers, right? Rather than rewriting every contract from scratch, let's feed the let's augment the LLM with our last 100,000 contracts and then try to to input parameters that we'd like for the next contract coming up, and so certainly there the conversation is directly relevant in terms of are you putting in the right contracts? Are you covering the space of contracts that you want to write? Kind of thing. Are you putting in enough of them? Are you do you want to write contracts in the United States or in the English speaking part of the world or all over the world? So do we have the contracts that will properly augment the LLM so that we can we can form a good basis for interpretation, or excuse me, a good basis for prediction.
Yeah.
Right, Raj, you want to build on that?
Yeah, I do. If we think about Chat GPT, the other LLMs, they're based on the internet. They use the whole internet. Now, we know there's a lot of bad information out on the internet. If you don't believe me, check out the information on the internet. So you're going to get some bad results. LLMs are going to say that I'm the vice president of Baxter International and I've never worked for them. The future, I think, of these large language models is not building them on the internet for that very problem, but rather building them on carefully chosen sets of data that might be unique to a given organization's needs, where they can validate the data, ensure that it's close to the right data, and get a useful result out of it. So I think it's not a matter of getting more data, it's about getting less data, but getting the right data so the LLM actually works well.
Yeah, and that's really an excellent point, right? I mean, the future may very well lie in small language models, right? Tailored to do this, tailored to do that. And think about if you had a choice, across your company of a small language model associated with the 50 most important things you do in your company, or one large language model. Right. I mean, like the researcher may, like this is really great and elegant, but the small language model is I guess I think it's the equivalent to sort of a shotgun versus a high-powered rifle. And if you have a high-powered rifle to shoot down a particular problem, don't use the shotgun. So I agree with Roger. I think the future is in smaller language, tailored things, and by the way, and also with statistical twins, so that we can understand these things, right? One final comment on this, and I find the choice of language really interesting. Business people understand that models make mistakes, right? I mean, because people make mistakes and so forth. right? But hallucinate, and a lot of times, we describe all the errors in an AI as a hallucination, right? But some of them aren't. Some of them are just we got it wrong, as opposed to hallucinations. But hallucinations is not the kind of word that you want to use to build trust with, with serious business people. Oh, right, I went off, back. Um, but it builds on the point. It builds on the point about having explainability, about having targeted things, right? About having a basis for inference that that takes something that. And by the way, it's not just it sounds offensive; it really is offensive. Anyway, okay.
So, last question. We're unbelievably already out of time, and hopefully you can answer this quickly because we're close to the end. But Ravi says having right data can be a continuous process. Can you provide some frameworks or best practices to evaluate right data that we collect on a daily basis?
Well, it's tough to do that because of the fact the right data depends on the problem you're trying to solve. And a lot of times people collect everything they can measure without carefully thinking through, why are we collecting this data? What's the purpose? So it's not a bad idea to collect everything you can measure, but just realize when the real problem is defined, the data you collected may or may not be what you actually needed to solve that particular problem.
Yeah, I was just going to build on one thing. Is that Roger mentioned statistical process control, and people who've seen it in action, like you never go back. I mean, it's just this incredibly powerful, simple tool. But right, so you train a model on this domain, and then over time, the data may be going outside of that domain, and statistical process control is ideally suited to raising the flag. You're in a comfort zone. You're in a zone we understand. Versus, maybe not so much.
Well, Roger and Tom, thank you both so much. Such an interesting look at AI from a very, important and grounded perspective that everybody's wrestling with, and figuring out. One of the things that occurred to me as you were talking about the team is to be able to ask dumb questions when you're crossing over those different functional areas. That takes some psychological safety and building. There has to be some time put toward building the team and building those relationships. So thank you so much, and thanks to our sponsor SAS for supporting this event. Have a great rest of your day. Thanks so much.
Thank you.